Okay, let's talk about timing gates. These are typically used to measure velocity. Make sense? Well, we'll talk a little bit more about measuring velocity and do so with the framework of measuring a 40-yard dash time. Well, 40-meter dash, let's just keep it meters. So what do we have for a sprint test? We have a course set up where there's a start line at 0 and an end line at 40, and we'll call this meters. And then we have a runner. Let's see if I could draw a runner here. On the start line, maybe they're not standing like that, but that's the best I can do drawing-wise. And we have some system set up that is triggered when the runner starts running, and then it's stopped when the runner crosses the finish line, and it continues even running beyond that stop line. So or finish line. You're not stopping at the 40-meter mark. You're continuing to go beyond it. And so the initial velocity of the person is 0 meters per second, and the final velocity, we don't know what that is. So what do we know? Well, we set up a timing light system, a very common way to do combine testing. They are just systems that are, it's just a switch, where the switch is turned on or off, whichever way, when a beam of light is broken as a person passes through it. And again, we can set this up where we can get a time here of 0 seconds, and then we go have the runner finish and crosses the finish line, and maybe, just for the sake of doing math, let's say they finish in 4 seconds. So they covered 40 meters in 4 seconds. So we can calculate the velocity as displacement over time, or 40 meters over 4 seconds. And so the velocity is 10 meters per second. It's positive because velocity is a vector. Yeah, we don't typically add that in when we're doing our combine testing, but 10 meters per second. So now let's figure out, where did that person run 10 meters per second? What's the velocity right here? It's 0 meters per second. What's the velocity at the end? Well, it's not going to be, most likely, it's not going to be 10 meters per second. So let's think about this a little deeper. Let's draw out just a simple velocity plot here, and I'm going to put position on the x-axis. Okay, a little different than what we usually do, where we put time down here, but this is okay. And we know that the person completed the 40 meters in 4 seconds. So how do we represent that here? Well, here's 40 meters, here's velocity, and all we can say is the person ran at 10 meters per second overall to complete this 40-meter sprint. That's all we can say. That's the sophisticated nature of this plot. But what's interesting is we know this point right here. Velocity initially is 0 meters per second. So to start at 0 meters per second and have a velocity overall of 10 meters per second, I need to have somehow run faster than 10 meters per second. And so really what we calculated here is what's called average velocity over that distance. And I'm going to do this, it's not necessarily correct, but I'm going to draw this out to get that average of 10 meters per second. Knowing that I start at 0, I need to have run both slower and faster than that 10 meters per second. If I take the average of all the velocities along this point, I'll get that 10 meter per second average. So I didn't do a great job of splitting that in half, but And that if I just did this mathematical modeling, maybe they cross the 20-meter mark at 10 meters per second. But then they're finishing at a faster velocity. Now, does that really happen? Does that actually happen? Well, with one time light here and one starting time light here, we can't tell how fast the runner actually ran during the 40-meter sprint. All we can say is, on average, they completed that 40-meter sprint in at 10 meters per second. Now, I drew this line. Well, maybe it's something where they take off really slow and then they run really fast near the end, or something very different than that. There's lots of different iterations or different variations of the way that velocity can change during this 40-meter sprint. So how do we get to this understanding a little better, or understanding of runner's velocity? Well, when we do the same test, 0, 40 meters, but now maybe we put another timing gate at the halfway mark. And if we do that, then we're going to get a time between 0 and 20, and another time between 20 and 40. And we're going to get a little bit more detail, and maybe our plot now looks like, this is again position here in meters, here's 40 meters, here's 20 meters, and here's this velocity. And we know we're starting at 0, but now maybe I get it, now put a time right here, I get another velocity between 0 and 20 meters, and then maybe another velocity, well, not maybe, I will get another velocity between 20 and 40. So I get a little bit more information and see, oh, well, they're not running as fast between the 0 and 20 meter mark. That makes sense. They're speeding up. But then the second part of the run, they're running much faster. Okay? And overall, the average would still be, using the numbers from before, 10 meters per second. Okay, maybe we want to get a little more granular with detail. Maybe we want to try to identify where that peak velocity is occurring. So maybe we set up another timing light at the 10 meter mark and another one at the 30 meter mark. Now we're getting a little bit more detail. I'll draw that same plot down here. Position. Here's 40. There's a velocity. Now I'm still starting at 0, but now I'm getting a time for that first 10 meter interval. Let me put that here. 20, 30. I didn't space it out well enough, but that's okay. So maybe in the beginning, that's the velocity between 0 and 10 meters. And maybe they're running a bit faster between 10 and 20 meters. And then maybe a bit faster between 20 and 30 meters. But maybe they slow down. I did a terrible job of spacing these out. They should all be equal intervals. But then maybe they're slowing down in the last 10 meter segment of this sprint. So now we have an issue of someone running this fast to 10 meters, or between 0 and 10 meters, they're running faster. Between 10 and 20, they're running fastest in terms of this model, between 20 and 30, and then they're slowing down near the 40 minute mark. But they still did the race, or the thing in 4 seconds, so they still have an average velocity of 10 meters per second. Okay, so this is a nice model, and it does require 1, 2, 3, 4, 5 sets of timing lights, or a zero, something to trigger all the timing lights, and then these other ones here. As we get more timing lights, it gets more expensive to do the test. We could also use a inertial measurement unit that samples the run throughout the 40 meters, and not setting up actually timing gates at this point. But now we use an IMU unit, or maybe a GPS unit, that's sampling at maybe 50 hertz, 50 samples per second. So if I did this in 4 seconds, if I'm sampling at 50 samples per second, what's that? That's 200 samples. So rather than getting 4 time intervals, or really 5 because we got 0, I've got 1, 2, 3, 4, 5 times. Rather than just getting 5 times, I'm getting 200 times. Okay, and now I could start looking at my velocity profile. This is position again. This is velocity, starting at 0, and now I get 200 measurements of what's going on during the run, and maybe it looks like something like that. And I'm trying to draw 200 dots, 200 samples. Now again, the average, all right, let me do it this way. The average is still 10 meters per second. But now, using this system, I'm able to identify, oh, here's a peak velocity, and that peak velocity occurred at this position during the run. So now I have a more granular level of detail of how velocity varied during the course of a sprint. And you may say, well, what's the best sprint strategy then? Well, for doing these types of sprints, it's actually been some really neat research on this, is you want that peak velocity to occur somewhere other than at the end of the race. Because if you're reaching the end of the race and you're only then hitting your peak velocity, all the other velocities are slower than that. So somehow you want to try to reach that peak velocity, and the shorter the race, the sooner you want to try to reach that peak velocity. The longer the race, that isn't necessarily the case. All right, but there's a lot of good data out there on sprinting, and this is very characteristic that we actually start slowing down near the end of a sprint. And how much we slow down? Well, it just depends on the sprinter's fatigue resistance and so forth. Okay, so but now this is doing something with an IMU unit, GPS unit. Why don't we use this in a combine type of test? It's a numbers game. It's a how many people can we process in a particular period of time? When we've done some combine testing of youth sports and we have 200 kids, we can't set them each up with a GPS unit, run them 40 meters, download the data, and then put the GPS unit on the next athlete. That's just too time consuming. It's very quick to use timing gates, but the limitation of timing gates is we get limited information, and that amount of information we get is all dependent on how many timing gates we use. The more timing gates, the more data, the more expensive the test becomes. Okay, so that's a little bit more on timing a sprint. Okay, thank you.